All right. Oops. Hey guys, 6.3 day 3 today. So I'm just going to review both of the types of problems that we did and go through a couple other ones that are a little more challenging with shifted axes of rotation. I hope you had a wonderful weekend. Today, or this week is a short week because Friday's another reading day, and then we have Memorial Day weekend. So today's the last lesson. You'll have a worksheet on Wednesday, and then the quiz won't happen until after Memorial Day weekend. Okay? So just a review, we've seen this before. If the axis of rotation is horizontal, then the radius will be in terms of x. And that happens because if we have a horizontal axis, we have a vertical rotation, and therefore the radius is running vertically up and down, which is a y equals. Y equals is in terms of x. And then the opposite would be true if the axis is vertical. You then have that horizontal rotation, that carousel, which means that we have x equals radius, which is in terms of y. We always would add or subtract a constant to find that volume. And when I'm talking about add or subtracting a constant, that means if the axis of rotation has shifted, did the radius get smaller or did it get bigger based on that shift? Okay, so first example here, we have the two-dimensional image as well as the three-dimensional image with the axis of rotation. So y equals x, y equals root x, those are the two functions. That's what's giving us our bounded space. That right there. And if we rotate that bounded space about the line, y equals 1, the nice thing here is that bounded space with y equals 1 is the point of intersection. Okay, so that keeps it, from too many complications. So the first thing that I would reflect if I was just doing my two-dimensional graph, I would probably do the line first. The line is below the curve in the original graph, which means it would be above the curve in the reflected graph. Okay, and this is that two-dimensional graph showing the reflected picture. Yes, Griffin? We're going to have ice cream as soon as I'm done with the video.
Yes.
Okay. All right, so now you can imagine this rotating. So in order to get that disk, as we see in the second picture on the right, we have curve rotating to curve, line rotating to line. The inside circle is the distance between the curves. That's what we're going to subtract away. The outside circle is the distance from the lines. Okay, so we have a big R and we have a little r. Big R is made up by the lines. Little r is made up by the curve. Okay, and it's all about the distance from the axis of rotation to the original curve is the way I most like to think about it. So that would be an example of what my radius would be. Okay, so I'm going to cut it, lay it flat. Because of my axis of rotation is above the original curves, I'm actually going to draw it downward. But it's still a y equals, so it's still going to be in terms of x. Top minus bottom here. Axis of rotation is actually the top function with that radius. So top minus bottom. That's how I'm finding my radius. That gives us the distance. Right? So top is 1. Bottom is the line, y equals x or x. For the little one, same idea here. 1 is my top, root x is the bottom, is the curve. So now, my pi, big R squared, minus little r squared. Careful with all of your parentheses, end it with a dx. Final step, x's are on the inside, so we need to go to the x-axis, furthest left value, furthest right value, 0 until 1. All right. So this is going into Desmos. Zero until 1. Put the pi over here. Again, it doesn't really matter where you put the pi. You can put it inside or outside. Just make sure it's not inside the parentheses at all. So 1 minus x squared minus 1 minus root x squared dx. Let me double check 1 minus x squared. 1 minus root x squared, 0 to 1. Good, so 0.52 is going to be our answer here. Okay, that's the volume of this sort of cone-shaped object. Right, the only part that's actually solid is that small sliver, and of course it runs around the entire cone, but the entire inside is going to be left open, which is why, part of the reason why the volume is so small. So I crossed this out, not that it's a bad problem. If you want extra problems to practice on your own, it's a great problem. It's just we don't need this many in our lesson. Okay, so here's the second one. Now we have these written as x equals equations. Okay, the graphs are given. X equals y squared is essentially a sideways parabola. Okay, if you need to graph that in your graphing calculator, you're going to have to graph it as y equals positive root x and y equals negative root x. And the x equals 1 is not something that you could put in the graphing calculator. It's sort of like a domain restriction. Desmos, you can graph these exactly as they are. Okay, the axis of rotation is also the line x equals 1. Okay, so that makes this problem a disk problem. It's not a washer. I might have misspoke before. The previous one was referred to as a washer. Anytime there's a hole in it, it would be a washer. Anytime it's a solid, it's a disk.
Can I tell you something?
Sure.
I'm gonna have Lucky Charms right now.
No, Griffin, I need to finish this video, okay?
Daddy, can I have Lucky Charms?
Sure. Okay, so in this case, we have a solid, and if we're reflecting it about x equals 1, right, the parabola is just coming over here, getting the same exact shape, and it's spinning. Okay, like that. So when we cut it and turn it, our radius is going to run horizontally, okay, which makes our radius an x equals. In this case, we only have one radius. We don't have a washer. We're not subtracting anything. Distance from axis of rotation to curve. Instead of top minus bottom, it's right minus left because we're moving across the x-axis in that manner. So right would be the line x equals 1. Left would be the y squared. So that would give us that distance at any given moment along this curve. 1 minus y squared. Okay, dy. There's y's on the inside, so we go bottom y value to top y value. And that's going to be from -1 until +1. That's 4.19. Okay. Okay, again, not a bad problem, just don't need another practice problem. So try that on your own if you'd like to. And then I have, I think just, this is the last one. Nope, 2 more. Okay, 2 more. Region A about the y-axis. Okay, so here is region A, bounded by the pink curve of y equals x squared plus 2, the horizontal line of 6, y equals 6. And we're rotating it about the y-axis, which means that it is reflecting here and here. We have a solid, and it's spinning like that. It's a carousel problem. Okay, so the radius would be a right minus left, the axis of rotation is just x equals 0, or the y-axis, so we don't have to worry about that. The radius is just going to be the function y equals x squared plus 2, but we do have to acknowledge that we have to solve it for an x equals, right, because it's running that way. So side work, subtract your 2, and square root. So pi r squared is the area of a single circle. We integrate it for our volume. From bottom y number to top y number, 2 to 6, based on the graph. So make this a little bit easier in the calculator. Pi, 2 to 6, y minus 2, dy. $25.13. Okay. Last one. So now we are going to rotate this about the vertical line x equals 2. Okay. Region A again. So we're taking this sort of portion of the parabola and we're reflecting it. Okay. And the y-axis is going to reflect with us. So here is the corresponding matching space. Okay, at first glance, reading this, it sounds like the problem isn't so tough. But it is a little bit harder than the previous one. So the y-axis and its reflection are essentially our outermost bounds, and they have the outer circles happening. Right? And then the curve is also rotating curve to curve. And that is the inside, making this a washer problem. Okay, so we need a big R, we need a little r. Horizontal, we need them as x equals. The other thought with this horizontal x equals is it's right minus left. Axis of rotation minus curve. Distance from axis of rotation to the curve is your radius. So the axis of rotation is 2. So 2 all the way to the y-axis, well, that radius is always 2, right? 2 minus 0. Okay. The second one, distance from axis of rotation to the parabola, right? We had already solved this, y equals x squared plus 2, as x equals square root of y minus 2. So now this one is 2 minus square root y minus 2, this short distance here. Okay. So big integral, pi, double parenthesis, because we have big R squared, which is just 2 squared, minus little r squared, which is 2 minus root y minus 2 squared dy. Now in this problem, limits of integration are still 2 to 6. I wouldn't go about simplifying it. Yeah, you can change the first one to a 4. 2 squared is 4. But the second, you would have to FOIL it out. So don't do that. Don't distribute that squared. That would be incorrect. This is not turning into 4 minus y minus 2. Just leave it as is. Okay, so I'm going to work with the integral that we had before. So we have a 4, I said that's fine to go with that, minus, parenthesis, square root, y minus 2, no, I'm just going to 2 minus square root y minus 2, parenthesis squared, parenthesis again, dy. So 41.89. And that looks good. All right. So that's it for chapter 6, you guys. Again, you'll have worksheet, quiz. I'm going to post office hours for this week. I'll post office hours for Wednesday. Hopefully that gives you enough time to watch this video, kind of formulate your questions, and then while you're doing the practice worksheet on Wednesday, if you have any questions, I'll be available to give you all a hand. So I'll post that. I'm going to make myself available, I don't know, I think maybe 11 o'clock or so, 10, 11 o'clock. But if you need me at a different time, just reach out. Let me know. I'm flexible. Okay? Take care, guys. I'll talk to you soon.